Hi everyone, today in this video I'll walk through activity 2.6.4 and I'll be demonstrating 6 different matrix transformations and explaining how each one of them affects our character. For each part, I'll explain how the transformation was chosen, why the matrix is correct, and what effect it has. So for part A, we begin with the general homogeneous matrix we used for 2D transformations in 3D homogeneous spaces. So it's given the matrix ABCDEF001. This form lets us combine rotation, scaling, or shearing, and translation all into one matrix. And the third row ensures that the plane stays the third row ensures that we stay on the plane z equals 1. When multiplying the matrix with the points x, y, 1, we get the new points x prime, y prime 1, where x prime and y prime depend linearly on x and y, and this sets the stage for all the transformations we do in later parts. So in part B, we have a translation by 2, 2. We move the character up, right 2 units, and up 2 units. In the homogeneous coordinates, translation is achieved by putting the values in the last column of the matrix. We know this is correct because multiplying the matrix by any point x, y, 1 results in x plus 2, y plus 2, 1, and this matrix preserves the shape and orientation while shifting the position. And in part C, we have a reflection across the y-axis to reflect the character so their waving hand switches sides. So we reflect across the y-axis. This means we flip all x values while keeping the y values the same. The matrix is correct because the -1 in the top left reverses the x-coordinate. Any point on xy becomes -xy, which mirrors the figure horizontally. In part D, we're looking at a clock wheel with 90-degree clockwise rotations. As the character performs a cartwheel, they rotate 3 times by 90 degrees clockwise. So the matrix for the rotation would be 0, 1, 0, -1, 0, 0, 0, 0, 1. And we use this matrix 3 times in a row. Each application rotates the character further. It's correct because we derived it from the right-hand rule and standard rotation definitions. So for part E, we're zooming in on the face. This scene involves both translation and scaling. So first we move the character down to the center of the face using the following matrix 1, 0, 0, 0, 1, -2, 0, 0, 1. And then we zoom in. Then to zoom in, we scale the figure up uniformly by applying the matrix 2, 0, 0, 0, 2, 0, 0, 1, 0. Sorry, 0, 0, 1. This pair of matrices is correct because the translation repositions the head to the origin, and scaling by 2 enlarges it equally in all directions. Composing them gives us the full effect. And finally, for part F, we are casting a shadow. To simulate a shadow, we flatten the figure onto an x-axis by removing all vertical information. The following matrix for this is 1, 0, 0, 0, 0, 0, 0, 0, 1. The matrix zeroes out the y values of every point. Since shadows only vary in the x direction, this effectively projects the character flat onto the ground. And in part G, we are asked to write a final scene to the movie and describe how to construct a sequence of matrix transformations that create your scene. I'm sorry, 1 second. So to start off, we have the jump, which I've written here at the top. It translates up by 2 to simulate the lifting off. And then the second matrix I have is the flip midair. The second matrix here is a reflection across the y-axis where they raise their other hand and drop their other. And then the third matrix is the cartwheel that they did, where there's 4 matrices and each one was a 90-degree rotation clockwise. And the fourth one is the zoom in, where we enlarge the character by 1.5 times their normal amount. And finally, the shadow projection, which matrix C is written right there. So each of these matrices was selected based on the intended movement, translation, change in position, or rotation after orientation. Composing them in sequence achieves a smooth, celebratory jump and landing. Thank you for watching my video. Each transformation in this activity builds on to the previous, and together they show how powerful matrix operations can be in animating motion. I hope this explanation helped you understand both how and the why behind each transformation. Thank you. Have a great day.